Okay. Well, I want to present you today our project idea regarding acoustic emission process databases for laser texturing process control. The main idea behind it is to look at how a laser process, which is usually very precise, can go wrong. And while the process is very precise, it also requires that we keep also a very tight processing window of tolerances in order to make sure that the parts we manufacture and the textures we process are according to specifications. And some of the things that can go wrong in laser processing is, for example, a focus drift. This can happen due to a multitude of reasons like optics warming up or a laser pointing error. We can also have issues with incorrectly set parameters of the laser, like the repetition rate. We can have sample tilt, or, for example, power loss, which can happen natively by the laser or due to damage over time by optical components. And all of these issues can lead to surfaces not being according to the specifications. And in the standard way of doing this, we only find out after the process by using a confocal microscope or a scanning electron microscope, where we can then observe the surface ex situ. But this is, of course, time consuming. The equipment is certainly expensive, and we gain the knowledge only after the processing, so we have no chance to correct it. And what we are proposing is to actually look at emissions that we have during the process, which are, for example, acoustic emissions. These are generated by the expanding plasma during the laser processing, which generates shock waves that we can actually listen to. And these contain some information that we can utilize in order to extract information about process quality and accuracy. And the big advantage is we can do this with every sample, and it doesn't cost additional time. Here you can see what information we can theoretically extract from this acoustic monitoring. Here on the left, you see an example acoustic monitoring module mounted to a laser texturing setup. We can analyze the signal in the time domain and in the frequency domain, and we can find all sorts of correlation. For example, in the past, we've seen that frequency and pulse overlap, of course, correlate to characteristics of the signal, but also the focus of the process, as well as the depth of the structures fabricated by the laser, can correlate with the acoustic emission. And so we want to generate this acoustic fingerprint as a way to infer the quality of the process in situ. And what do we want to do in this project? Well, we want to build process maps where we link acoustic emissions to all sorts of process parameters as well as material systems, because different materials generate different acoustic emissions during the processing. We want to look at coating and coating removal as well as at different texturing approaches. And the main benefit for the partner that would be interested in using this technology is, of course, we can automate machine setup with acoustic monitoring. We can ensure the quality. We can reduce scrap as well as trial and error during the processing. And we can quantify what has before only been the domain of expert knowledge. And the project phases for this will look roughly like this. In the beginning, we will start with setup and the integration of the acoustic monitoring. And then the big part is, of course, the data generation, where we will texture according to a design of experiments, a lot of different surfaces, extract the acoustic signals. And then in the second big block of the project, we would analyze this data and characteristics of the acoustic emission to then build a database of acoustic signals correlated to the outcomes of the surface, which then can be transferred to industry partners that could use this to automate their processes and monitor their processes for quality.